Welcome to The Explainer. I am absolutely thrilled to have you here today because, well, we're diving into a massive, honestly kind of absurd double standard in modern physics. It's literally created a heavyweight showdown. You see, for decades now, we've allowed general relativity to explain the big stuff, right? And quantum mechanics gets to cover the small stuff. But here's the thing. The universe doesn't have a split personality. This glaring, missing, unified description is exactly what brings us to today's ultimate showdown. The intense experimental race testing quantum gravity theories against some radical, emergent deterministic frameworks. To really grasp the massive stakes of this investigation, we have to look at the absolute extremes of the universe. I mean, think about it. Can a black hole actually be destroyed? And if so, do we even possess the tools to do it? When we take our best, most reliable theories, general relativity and quantum mechanics, and apply them to extreme environments like a black hole, neither theory fully holds up. Basically, the math just breaks, and the thing pulling them apart, the very thing tearing our understanding of the universe at the seams, is that missing quantum description of gravity. We're talking about the single most important unsolved problem in modern physics here, something that's been fiercely debated for over 50 years. And this brilliantly illustrates exactly why the math breaks down. On one side, we've got general relativity, which beautifully describes the really large stuff, portraying reality as this smooth, continuous, predictable fabric of space-time. But then, on the flip side, we have quantum mechanics. And quantum mechanics insists that everything is made up of discrete, individual, totally random chunks, or quanta. The problem is, you just can't fundamentally describe reality as a smooth, continuous sheet and a chunky pile of pixels at the exact same time, without some deeper underlying framework. Actually, scratch that, it's more like a tense clash of paradigms right now. In one corner, we have mainstream scientists desperately trying to force gravity into the quantum realm, hunting for these theoretical particles called gravitons. But in the opposing corner, radical determinists proposing that gravity isn't even a fundamental force at all. To them, it's an emergent illusion. And the crazy part? We are finally building the physical experiments to test who's actually right. All right, let's get into Section 1, the physics breaking point. Moving right along to Section 2, mainstream corner, tuning fork quantum tests. Okay, let's dive into this mainstream approach by looking at a genuinely groundbreaking experimental blueprint from a group led by researcher Igor Pekovsky. Look, if we can't build a particle collider the size of a galaxy to isolate a single graviton, well, maybe we can see the indirect evidence of its work. How? By mimicking space-time using a material that has very strong quantum properties. To actually pull this off, they rely on a wild concept called superposition. You can think of superposition as this fuzzy quantum state where an object literally exists in multiple states at the exact same time. So, for this specific experiment, the scientists want to put a microscopic object into a state where it's vibrating and remaining perfectly still simultaneously. I know, it's a completely mind-bending concept, but it's grounded in a very tangible, real-world setup. According to our sources, this setup involves, and I quote, a microscopic metal bar similar to a tiny tuning fork that would be cooled to nearly absolute zero. Okay, so once it's completely freezing, they use lasers to kick that tiny bar into that fuzzy superposition state we just talked about. Pekovsky's argument here is that if gravity really does have quantum properties, it could subtly alter the superposition of this microscopic fork. Basically, the researchers are hunting for a telltale quantum imprint left behind by gravity. Even if they don't catch a graviton red-handed, finding this imprint would absolutely prove that gravity behaves like a quantum field. Section 3. Let's move to and see how this builds into the entanglement sink experiments. So this brings us to the quantum sink test, which was actually proposed simultaneously by two different teams back in 2017, including researchers Chiara Marletto and Vlatko Vidral. Now, instead of hunting for a particle of gravity, they're trying to figure out if gravity can act as a quantum connection, like a channel between two distinct objects. The physical procedure for this is, well, it's incredibly precise and exceptionally difficult. Step 1. You take two microscopic gold beads, suspend them, and put their positions into an uncertain quantum state. Step 2, you have to completely isolate these little masses from literally all other possible forces. I'm talking electromagnetism, thermal noise, the whole shebang. Everything except for gravity. Then, step 3, you just wait. You wait and hope that the two beads become quantumly entangled, meaning their properties become perfectly correlated across a distance. The challenge here is just immense. If you go too small, gravity is too weak to measure. But if you go too big, there is no way you can maintain that fragile quantum state. But think about this. If they actually pull it off, the core hypothesis is ironclad. If entanglement occurs between those gold beads, and you can absolutely guarantee it happened through gravity alone, then gravity itself has to be a quantum mediator. That would be a massive, completely historic victory for the mainstream paradigm of quantum gravity. It would be a total game changer. Which brings us to Section 4. Enter the finite observer. But what if these quantum gravity experiments just fail entirely? What if gravity isn't quantizable because, well, it isn't a fundamental force to begin with? What if it depends not just on the universe, but on the thermodynamic and computational limits of us as finite observers within it? Now, what's really interesting about this slide is how it maps out these alternative emergent frameworks. They treat gravity not as a fundamental particle, but basically as an artifact or an illusion. For instance, you have the cellular automaton theory, where gravity is just a macroscopic average of deterministic, microscopic fast variables. Then there's holographic error correction, treating space-time like a redundant code on a boundary. And finally, you have the finite observer theory, which argues that reality is actually a static, n-dimensional relational geometry, and the gravity we feel, it's just an entropic projection caused by our own algebraic restrictions. To really wrap your head around finite observer theory, you need to understand something called the dimensional partial trace. You see, because we are physical beings, we have a strictly finite capacity to process information. We literally cannot see the underlying, discrete, n-dimensional quantum substrate of the universe. So mathematically speaking, we are forced to compress or trace out those unobservable dimensions. According to this theory, the continuous 4D spacetime we experience every day, along with mass and gravity, are strictly macroscopic illusions. They're basically entropic artifacts of our own inability to process the whole picture. All right, on to Section 5, baryonic entanglement bounds. Now, I know this sounds a bit like abstract philosophy right now, but hear me out. These deterministic theories actually come with strict, testable mathematical boundaries. If gravity is really just an informational illusion created by the entanglement entropy of local matter, then there is a hard mathematical limit on how that illusion of gravity can behave at galactic scales. Just look at this. We can actually visualize the topological severance limits here, literally counting the theoretical limits of ingoing single particle modes being sent into a singularity from a localized time band. Long story short, if gravity is an emergent informational artifact, it absolutely must obey these precise topological and computational limits. And the coolest part? Scientists can test this illusion right now out in the cosmos. They can analyze the Mond radial acceleration relation, which, by the way, emergent theories perfectly predict without even needing dark matter. They can measure the Hubble tension to gauge topological asymmetry. They can even look at galactic rotation curves to see if the anomalous acceleration profile violates the structural entanglement bound. If they go out and observe a violation of these strict macroscopic bounds, boom, they can completely falsify the emergent theories. So yes, this showdown is entirely 100% testable. Let's wrap it up with Section 6, the ultimate gravity showdown. So we have officially arrived at the ultimate showdown. On one side, we have physicists chilling tuning forks and suspending microscopic gold beads. On the other side, researchers looking outward at the massive boundaries of galaxies. And you know what? The ultimate proving ground for these competing theories might just be singularities. Right here, we're seeing examples of naked time-like singularities approaching their geometric limit. The thinking goes like this: if the universe's fundamental dynamics are actually governed by deeper mechanics, like underlying pseudo-random quantum circuits and holographic codes, then things like naked classical singularities might be mathematically forbidden from even existing without an event horizon to hide them. These extreme astronomical phenomena are literally the exact laboratories where the continuous fabric of relativity and the discrete chunks of quantum mechanics are fighting for absolute dominance. So, the crucial point is this. What happens if the quantum experiments completely fail to find entanglement? And what if the macroscopic observations of galaxies perfectly match the baryonic entanglement bounds? If that happens, we are looking at perhaps the largest paradigm shift in the history of science. Let that sink in. It would mean gravity isn't a force, it isn't a particle. It's actually a thermodynamic illusion generated simply by our own limited ability to perceive the universe. That is huge. I want to leave you with this wildly provocative question to chew on. What if reality isn't just something happening to us? What if the very fabric of space, time, and gravity depends not just on the universe out there, but on us as finite observers processing it? It's a lot to think about, right? Anyway, thank you so much for joining me on this explainer today. Keep learning, keep questioning the systems and the space-time around you, and I will catch you next time.